Solution of radial equation of hydrogen atom problem in quantum mechanics leads to a differential equation of this form: x y double prime plus beta 1 minus x y prime plus alpha minus beta y is equal to 0, where alpha beta are in general a real number. This differential equation is known as associated Laguerre differential equation. Laguerre differential equation. Note that x is equal to 0 is a removable singular point. X is equal to 0 is a removable singular point of this equation. In earlier cases, we have solved Laguerre and the Hermite differential equation. In both these two situations, x is equal to 0 was an ordinary point, and we use power series method for the solution of first or second order linear homogeneous differential equation. This is again a linear homogeneous second order differential equation. The singular point of this equation is x is equal to 0, and any other finite value of x is a regular point. So the region of interest of this differential equation could be 1 x less than plus infinity greater than equal to 0, one option, and the option 2 is x is greater than equal to 0 and less. But as we have already stated that this equation arises from R equation, R equation in hydrogen atom problem in quantum mechanics, and the range of R is from 0 to infinity. So the region of interest of this differential equation is this. So the x is equal x between infinity and 0 is the region of interest. Now, if we put beta is equal to 0, we get the simplified version of this. With beta is equal to 0, this equation reduces to x y double prime plus 1 minus x y prime plus alpha y is equal to 0, where alpha is a real number, and this is known as Laguerre differential equation. And in general, as we shall show afterwards, any solution for any alpha value, real alpha value, diverges asymptotically, and the finite solution or the physically acceptable solution of this differential equation is known as Laguerre differential equation. So we start with Laguerre differential equation, which is this. With alpha will any real number. Since x is equal to 0 is a removable singular point, as per Frobenius-Fuchs theorem, we opt for a solution of the form with C0 as not equal to 0. We then plug this equation into this and get x summation over k ck n plus k plus k minus 1 x to the power n plus k minus 2 from this term plus 1 minus x summation over k ck x to the power n plus k minus 1, this is from this term, and then alpha summation over k ck x to the power n plus k is equal to 0. Now, if we rearrange the term, we see that this leads to a power x to the power m plus k minus 1, which is another, which has another contribution. Sorry, I have missed a term, m plus k over here, which has a contribution from this, and we write summation over k ck. This is m plus k is common, in which case we have m plus k minus 1 and plus 1, so this makes it m plus k square x to the power m plus k minus 1, and this term minus ck m plus k from here, and minus alpha x to the power m plus k is equal to 0. This is an identity and in x. So had it been the solution, correct solution of this differential equation, then it is, this relation is valid for every k. That is to say, the coefficient of every power of x to the power, coefficient of any power of x in this equation should be 0, as the right hand side is 0. For initial equation, we collect the lowest power of x in this expression, that is x to the power m minus 1, the power of x to the power m minus 1, which comes from this term only, and that too with k is equal to 0. So we get c0 m square is equal to 0. Since c0 is not 0, the solution is m is the repeated root, and m is equal to 0 and 0 are the repeated roots. The recurrence relation with this equation simplifies to summation over k ck x to the power ck k square x to the power k minus 1, and we take it on the other side. Summation over k ck k minus alpha x to the power k. Now the coefficient of x to the power k, recurrence relation, we obtain the coefficient of x to the power k. So from left hand side we get a contribution to x to the power k, when k in this side is replaced by k plus 1, so we get c of k plus 1 into k plus 1 whole square, and right hand side contributes to x to the power k for k is equal to k, and we write it minus alpha minus k, or c of k plus 1 is equal to minus alpha minus k plus 1 whole square ck. Knowing k is c0, we can get c1, and from c1 we can get c2, and the series can be generated in this fashion. Note that in the earlier two occasions we found a relation between ck plus 2 with ck. So there was a jump in or power. That is to say, in the case of Legendre or Hermite polynomial, Hermite differential equation, the solution were either even or odd. But here, since the even as well as odd powers of x are involved, the solution has no parity, no definite parity. Indeed, the question of parity does not arise in connection with the Laguerre differential equation, because here are ranges from 0 to infinity. So the question of parity arises when one takes an inversion about the origin. here no such situation arises. And so this is the solution, solid recurrence relation. As the region of interest is 0 to infinity, 0 to infinity, and we get for any real value of alpha, we get the solution in terms of an infinite series, because k is an integer and there is no question of getting a 0 in the numerator for general value of alpha. The numerator can be 0 multiplying alpha takes integral values. Now, as we have been habitual or familiar with the fact that whenever some infinite series arises in physical problem, one must check for its convergence. Otherwise, a divergent solution may not address a physical situation. So, our aim is to check for the convergence. So, we write the summary, and so we write ck plus 1 is equal to minus alpha minus k plus 1 whole square, ck as the recurrence relation. Now, the easiest solution, easiest test for convergence for infinite series is the D'Alembert ratio test. The D'Alembert ratio test, which we used in the case of Hermite differential equation 2, and found that the ratio test leads us to the truncation of the series. Let us use D'Alembert ratio test. We take two consecutive terms, uk plus 1 by uk, and take its modulus and let the limit k tends to infinity. So this becomes limit k tends to infinity ck plus 1 x to the power k plus 1 by ck x to the power k, where ck and they are related in this fashion. So it is limit k tends to infinity. This is, since we are taking the modulus, the minus sign is not required to be considered. Alpha minus k plus 1 whole square times x. If we divide both numerator and denominator by k square, we get a relation of this form. And when k is very high, this is 0, this is 0, so this is 1, and the thing effectively behaves as x by k. It may appear that as x k is very high, this term is less than 1, so the as per ratio test, the infinite series solution of Laguerre polynomial may be a convergent one. But recall that recall a function x to the power m e to the power x. This can be written as x to the power m summation over k is equal to 0 to infinity x to the power k factorial k. And this series is a known divergent series because e to the power x e to the power x has an exponential growth. This starts from 1, and this is the behavior of e to the power x. As x tends to infinity, it diverges. And if we take the ratio of two consecutive terms, if we call the term to be vk, if we call it summation vk k is equal to 0 to infinity, then vk plus 1 by vk, this is equal to x to the power m x to the power k plus 1 by k plus 1 factorial x to the power m x to the power k divided by k factorial. This x to the power m x to the power m goes, and this is k factorial plus k plus 1 factorial, and we have x on the numerator, and then this can be written k factorial times k plus 1, so this cancels out, and this is k plus 1, and for large k we can neglect 1 in presence of k, and when k is very high then this is x by k. So we see the asymptotic behavior of the infinite series solution of Laguerre differential equation is similar to the asymptotic to the behavior of the non-divergent series. So as per comparison test, we conclude that this infinite series solution of Laguerre differential equation has asymptotic divergence. So the conclusion is the infinite series solution of Laguerre differential equation has asymptotic divergence. And in physical situation, we are only interested with finite solution. So we look carefully into the recurrence relation. If we put alpha is an integral value, then there is a chance that the coefficient after certain term gets 0. As for example, if we put n alpha is equal to some integer, positive integer, and is equal to 1, in which case this becomes 1 minus k in the denominator. So let me if we choose a special value of alpha, that is alpha is equal to alpha is a natural integer, is an integer, and for example we choose alpha is equal to n equal to 1, in which case ck plus 1 becomes minus 1 minus k plus 1 whole square ck, and we see that C0 is 0 and C1 C0 is not 0, and C1 for C1 we need to put k is equal to 0, so we find that C0 and C1 they are not equal to 0, but C2, C3 etc. are 0. Similarly, if n happens to be 2, then C0, C1, C2 will not be in general 0, but C3 onwards will be 0. So what can we accomplish by choosing special value of alpha? If we put Cn in this line and n along for k, Ck in, and this is k, then the graph will be dry. This is the value of n. If we choose alpha is equal to n, then there is certain and then onwards it will be 0 right to infinity. So the infinite series reduces to a polynomial, and the polynomial solution is obviously a convergent one. So the asymptotic divergence of the Laguerre differential equation could be avoided by choosing special value of alpha, that is, in general, in Laguerre differential equation, alpha could take any value 0 to infinity. But if we want a finite solution, then alpha should have only special values, integral values, natural integral values. Note that the corresponding solution is known as Laguerre polynomial, etc. Recall that in the case of Hermite differential equation, we choose alpha to be 2n in the case of Hermite differential equation, and we choose alpha is equal to L into L plus 1 in the case of Laguerre differential equation. Here we choose alpha is equal to n in the case of Laguerre differential equation. There are different type of choices of alpha for different differential equation. So now the differential equation becomes the Laguerre differential equation with alpha is equal to n. The equation becomes x y double prime plus 1 minus x y prime plus n y is equal to 0, and the corresponding recurrence relation, that is this relation, becomes ck plus 1 is equal to minus n minus k plus 1 whole square ck. You will find in general that the book starts with this as the Laguerre differential equation, but now this has a finite solution. Asymptotically it has a finite solution, but this Laguerre differential equation has a finite series solution which has an asymptotic convergence. Now we come to the evaluation of the coefficient. For k is equal to 1, k is equal to 0, we get c1 is equal to minus n by 1 square c0. For k is equal to 1, we get c2 is equal to minus, here k is equal to 1, so n minus 1 2 square c1. If we plug in the value of c1, this becomes n into n minus 1, 1 into 2 square c0. For k is equal to 2, we get c3 is equal to minus n minus 2, here k is equal to 2, so it is 3 square c2. It is minus n into n minus 1, n minus 2, 1, 2, 3 square c0. So this is simply factorial 3. So this is minus n into n minus 1, n minus 2, factorial 3 square c0. We can find out in this way the general term. Going in this way, we get the general term to be minus 1 to the power k. Since for k is equal to ck plus 1, general term ck is equal to minus 1 to the power k, because c1 is negative, c2 is positive. In this way we get it as k factorial squared in the denominator. In the numerator we will have n into n minus 1, in this way n minus k plus 1 c0. So there are k terms in the numerator. We can write it as factorial n. The numerator can be written as factorial n divided by n minus k factorial. So this is n factorial k factorial C0. In fact, if we write the additional term, the next term will be n minus k, then n minus k minus 1, right to 3, 2, 1. And in the we adjust the following term in the denominator. So in the denominator we get n minus k factorial, and in the numerator it is n minus 1, right to 3, 2, 1. So that is n factorial. So this is the general term, which readily leads to the series for Laguerre polynomial. So we write Laguerre polynomial is defined to nth order Laguerre polynomial is one which satisfies the differential equation, these and having finite solution even in infinity, where ln x is given by summation over k is equal to 0 to n ck x to the power k, where ck is given by this relation, so this is k is equal to 0 to infinity, but c0 is taken out, so this is minus 1 to the power k n factorial k factorial square n minus k factorial x to the power k. Now there are two choices for C0. Choices for C0. One choice. C0 is equal to 1, which gives any order of Laguerre polynomial at the origin to be 1. The other choice is C0 is equal to n factorial, which leads to Cn ln 0 is n factorial. In the text you will find both the options, but here we shall opt for this one. So this is the solution for Laguerre differential equation. With C0 is equal to. So this is the series for Laguerre differential equation. Now if we want to find out few special values of Laguerre differential equation, we use this series expansion first. So the first we want to find out L1. So L0. So there will be single term and which is equal to k is equal to n is equal to 0. So we will have minus 1 to the power 0 factorial for this term, then 0 factorial square, and again 0 factorial x to the power 0, which is 1. Now come to L1. L1, in this case we put n is equal to 1 in this equation, and k has two values 0 and 1. So for k is equal to 0, the phase factor is 0. So this is 1 factorial. In the denominator we have 0 factorial square times 1 factorial x to the power 0. And for the second term, k is 1, in which case this sign is negative. And we will have again 1 factorial this times. This is 1 factorial square times 0 factorial x to the power 1. Since 0 factorial is 1, so this is 1 minus x. And L2, in which case n is equal to 2 and k has three values 0, 1, 2. So first term is k is equal to 0. This is 2 factorial 0 factorial square 2 factorial x to the power 0. For the second term, the sign is minus. It is 2 factorial 2 factorial, then it is 1 factorial square into 1 factorial x to the power 1, then plus 2 factorial, if this term is 2 factorial square times 0 factorial x square. Now when you see that it cancels out and this term is 1, this is 2 factorial minus 2x, sorry, yes, 2x, and this, for this term we have 2 and 4 in the denominator, so it is x square by 2. If we put x is equal to 0, we get both L2, L1, L0 both all are equal to 1. So in this way we can use the series method for series solution method for the solution to generate Laguerre polynomial. Now we come to Rodrigue's formula. As we have seen in the case of Hermite and Legendre polynomial, that the polynomial can be obtained, polynomial or the special function of a particular order can be obtained by n successive derivation and a differentiation of a known function, that is known as Rodrigue's formula. For Laguerre differential equation is as per the choice of C0 we opted here. This is e to the power where D, capital D stands for ddx. To prove this, we start with the right hand side. So right hand side is e to the power x n factorial, then dn x to the power n e to the power minus x. To evaluate this part, we use Leibniz theorem, e to the power x n factorial summation over k is equal to 0 to n n c k dk operating on x to the power n d of k n minus k operating on e to the power minus x. Now we consider this term dk x to the power n means k times successive differentiation of this. So if we write d of x to the power n, this is n x to the power n minus 1, d2 x to the power n is equal to n into n minus 1 x to the power n minus 2. So this is n minus 1 n minus k plus 1 x to the power n minus k. This we write as n factorial n minus k factorial x to the power n minus k. And the other thing, the d n minus k e to the power minus x. We know that d of e to the power minus x is equal to minus e to the power minus x. d2 e to the power minus x is equal to plus e to the power minus x. So we generalize it as minus 1 to the power n minus k e to the power minus x. So if we plug this into this equation, we get right hand side is equal to e to the power x n factorial summation over k is equal to 0 to infinity. For nck we write n factorial k factorial n minus k factorial. This is for nck, and for this we write minus 1 to the power n minus k n factorial n minus k factorial x to the power n minus k. Now, so there is n factorial square, one gets cancelled with this, and I have missed the e to the power minus x part. So this e to the power minus x cancels with this. So altogether we get k is equal to 0 to infinity minus 1 to the power n minus k n factorial k factorial n minus k factorial square x to the power n minus k. We introduced a new dummy index r, which is n minus k, and we write r is equal to 0 to infinity minus 1 to the power r n factorial, this is r factorial square n minus r factorial x to the power r. Here we have written n minus k to the r, and this sum up to infinity is being restricted because for a given n we can vary r from 0 to n, in which case this is 0 factorial, and negative integral values of argument, the gamma function is not defined, or factorial function is not defined. So effectively this becomes from r to n, so which gives you the series. If we use the series solution, this is nothing but the ln x. So we find the Rodrigue's formula for Laguerre differential equation. Let us apply this formula for the evaluation of Laguerre polynomial of few lower orders. L0 of x is equal to e to the power x by 0 factorial d to the power 0 x to the power 0 e to the power minus x. D to the power 0 means no differentiation is there, so this is 1. L1 of x is equal to e to the power x by 1 factorial, because this, then this is d to the power x e to the power minus x. So it will be differentiated once. This is e to the power x, and when we differentiate it we get 1, and when we differentiate it now L2, coming to L2 of x. This is the factor e to the power x by 2, and when we differentiate once, this is we get 2x, and when we differentiate this minus x square e to the power minus x. If we differentiate it once more, we get e to the power x by 2. When we differentiate this, we get 2 minus 2x times this, and when we differentiate this part we get minus 2x minus x square. Whole thing is multiplied by e to the power minus x. This part goes, and this is 1 when divided by 1, this double 2, and this is minus minus plus x square by 2. This is the same L2 that we have obtained using the series method. That's all for today. In the next class we shall start the generating function for the Laguerre polynomial.